Dear students, we are going to study algebra of complex number in this particular video. Let's start by studying what is meant by equality of two complex numbers. Let z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2 be the two complex numbers. Then z1 is equal to z2 only if a1 is equal to a2 and b1 is equal to b2. That means the two complex numbers are equal only if their real parts are equal as well as their complex parts are equal. Otherwise, we say that z1 is not equal to z2. One important thing to note is there is no concept of less than or greater than for the complex numbers. That means no complex number is greater than or less than other complex number. We can just say either they are equal or unequal. So no complex number is greater than or smaller than other complex number. Now, for example, if x plus iy is equal to 3 minus root 2i, then obviously x is equal to 3 and y is equal to minus root 2. The real part is equal to real part and imaginary part is equal to imaginary part. Now let's study next rule, that is addition rule. Addition. Let z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2 be the two complex numbers. Then z1 plus z2 is equal to a1 plus a2 plus I into b1 plus b2. So obviously we have added real part to real part and imaginary part to imaginary part. So this is the answer. Let's take one example. z1 is equal to minus 2 plus 3i and let z2 is equal to 8 plus 11i. Now what will be z1 plus z2? Obviously z1 plus z2 is equal to, its real part will be formed by the addition of the two real parts, which is minus 2 plus 8, and the imaginary part will be added to imaginary part, that is 3 plus 11i. So the final answer is 6 plus 14i. So this is the answer. Now we can try to understand this addition by using the Argand plane also. Remember, the rules of addition of the complex numbers on the Argand plane is similar to the addition of vectors, the triangle law of addition of vectors. We can use the triangle law as well as the parallelogram law over here. Now let's consider this example. So let's first plot the first number, which is equal to z1 minus 2 plus 3i on the plane. So obviously we have minus 2 over here and 3i over here. So this is the number z1. Now let's plot z2. z2 is equal to 8 plus 11i. So 8 on the real number line, right? And 11i on the y-axis, which is the imaginary axis. So okay, this is our z2. Now we have z1 and z2. Now we want to find z1 plus z2. So either we will add z2 to z1 or z1 to z2. So let's add z1 to z2. So this is z1 now, right? We have plotted the z1 from here to here, right? That is, we have started from the terminus of z2. So our final answer is here, right? So this point gives us z1 plus z2. So obviously you can see we have found out the addition by using this diagram. Now important point to note is, if z is equal to a plus ib, then minus z will be minus a minus ib. If we want to plot this on the diagram on the Argand plane, so this is z, real part is a and imaginary part is b. So obviously minus z will be exactly opposite to this, which is minus a minus b. So as we can see, length of z and minus z are same. So mod z is equal to mod of minus z. Modulus of both these numbers are same. But obviously what about argument? So they are exactly opposite. That means argument of z and argument of minus z differ by pi. Now in this case, this minus z, which is minus a minus ib, is called additive inverse of z, because as you can see, z plus minus z, right? This is called additive inverse because z plus minus z is going to give us 0 plus 0i, which is 0 complex number, right? Okay, so this is one of the properties of the addition, that is existence of the additive inverse. Let's try to study all the properties of this addition. Addition of the complex numbers, they satisfy the following properties. Let's try to understand these properties. The first property is the closure law. So before we start with that, let's consider Z1, Z2, Z3 be some complex numbers. Now we will try to understand the properties one by one. The first property is the closure law. The closure law states that the addition of the two complex numbers is also a complex number. The sum of complex numbers is also a complex number. See what is meant by a closure law? For a binary operation performed on two elements of a given set, if the result of the binary operation also lies in the same set, we say that the addition of that operation, that binary operation, follows the closure law. Here the binary operation is addition, and as we can see, we have Z1 and Z2 from the complex numbers, right? So we have two complex numbers taken from set of set of complex number, that is C. Then Z1 plus Z2 is also a complex number. That's why we say that the addition follows the closure law. Now the second property, we know that Z1 plus Z2 will be equal to Z2 plus Z1. That is the we can add the two numbers in any order and still we will get the same result. We call it as commutative law. Now associative law, Z1 plus Z2 plus Z3, right, gives us the same result if we add any two first and then add the third, right? So here if we want to add three complex numbers Z1, Z2 and Z3, if I add Z1 and Z2 first and then add Z3 into it, or if I add Z2 and Z3 first and then add Z1 into it, I will get the same result. This is called associative law. Now the fourth property, which is the existence of additive identity. Now what is meant by identity? Identity means for a binary operation finding an element which doesn't change the value of that original element. So here we have a complex number 0 plus 0i. Obviously the real part is 0 and the imaginary part is 0. This number is denoted by 0. This is a complex number and it is denoted by 0. Now this number is such that if we add this number to any z, any complex number, the result will be z again. Obviously the 0 will be added to real part and 0 will be added to imaginary part. We will get the same number again. Now the last property is existence of the additive inverse. So existence of the additive inverse. So for z is equal to a plus ib, which is a complex number, we have another complex number minus z, which is minus a plus I into minus b. This is a number such that z plus minus z will give us 0. This 0 is nothing but the additive identity. So we have another, for every z we have a number minus z such that z plus minus z will be equal to 0. So for every number there will be the additive inverse. So these are the properties which are followed by the addition operation. Now let's consider the third operation, which is the subtraction of the two complex numbers. Now if we know the addition operation and the additive inverse, I think it's very easy to understand the operation of the subtraction. Let's consider z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2. Then z1 minus z2 will be equal to a1 minus a2 plus I into b1 minus b2. That is, real part is added to real part and real part is subtracted from real part and imaginary part is subtracted from imaginary part. Example, if we have z1 is equal to 3 minus 2i and z2 is equal to 4 plus 6i, then z1 minus z2, right, which is z. So this z is equal to z1 minus z2, right, is equal to 3 minus 4 plus minus 2 minus 6, right. This gives us the result minus 1 minus 8i. This is the subtraction. Now this operation, which is z is equal to z1 minus z2, can also be visualized as z1 plus minus z2. That is, the additive inverse of z2, is added to z1. So Let's try to understand this operation again on the Argand plane. Let's first of all plot this number z1, which is equal to 3 minus 2i. This is z1. Okay, so this is z1 and this is z2, 4 plus 6i. Now how to find z2 minus z1? So first of all we will find minus z2, z1 minus z2 we want to find out. So this was z2, so this is z1 minus z2 now, minus z2, which is this is minus z2, right? Now what we are doing is we are adding this minus z2 to z1. This is z1 and this is minus z2, so this is our final answer, right? And this final answer is obviously minus 8i and 1. This is our answer. So again we have used the similar methods as we use in vector additions and subtraction. Now let's try to understand the third property, which is a third rule, actually multiplication rule. Let z1 is equal to a plus ib and z2 is equal to c plus id be the two complex numbers. Then the product z1 into z2 is equal to, actually this rule we can actually find out by actually multiplying the two brackets. We have a plus ib into c plus id. If I go step by step, then a into c plus a into ib plus c like ib into c, which is ibc, plus ib into id will give us I square bd, which is equal to ac minus bd. Why minus bd? Understand, I square is actually equal to minus 1. So okay, I square is equal to minus 1, so it is minus bd, ac minus bd plus I into ad plus bc. Example, if z1 is equal to 3 plus 5i and z2 is equal to 2 plus 6i, then z1 into z2 will be equal to 3 plus 5i into 2 plus 6i. We will multiply step by step now. 3 into 2 is 6. 3 into 6i is equal to 18i. 5i into 2 is 10i and 5i into 6i is equal to 30i square. But again I square is equal to minus 1. So what we have, 6 plus now this 18i plus 10i is equal to 28i and 30i square is actually minus 30. So 6 minus 30 is minus 24 and 28i. So z1 into z2 is equal to minus 24 plus 28i. Actually you can go this step by step or you can directly use this formula to find out this answer. Now there are some rules satisfied by multiplication of the complex numbers also. So these are the properties of the multiplication. Again the same properties. First is the closure law. So what does closure law states? That the product of the two complex numbers is also a complex number. That means if we take two numbers z1 and z2 from set of complex numbers, then z1 into z2 also lies in the same set of complex numbers. Then commutative law. What commutative law states? Z1 into Z2 is equal to Z2 into Z1. That is, the order of the multiplication of the two complex numbers doesn't matter. Either we can multiply Z1 into Z2 or Z2 into Z1, we will get the same result. Then we have associative law again. If we are multiplying the three numbers Z1 into Z2 into Z3, so Z1 in first, either you can take Z1 into Z2 first and then multiply Z3 to it, or you can multiply Z2 into Z3 and then multiply Z1 into it. Now the fourth rule, which is existence of multiplicative identity. Now what is multiplicative identity? We define a complex number. So there exists a complex number 1 plus 0i, a complex number for which the real part is 1 and imaginary part is 0. Real part is 1 and imaginary part is 0. This number is denoted by 1, as we can see. Now this number is such that if we multiply any number z by 1, we will again get z. You can try this multiplication, you will always get z again. So for every complex number z, we have z into 1 is equal to z. That means we have a number 1 plus 0i into set of complex numbers such that if we multiply any complex number by this, we will again get the same complex number. Now the next property, which is the existence of multiplicative inverse. So for every non-zero complex number, Z is equal to A plus IB. So what do I mean by non-zero complex number? That means at least A or B is non-zero. Okay, either A is or B. Both of them are not zero. So we have a complex number for this Z, which is defined by A upon A square plus B square plus I into minus B upon A square plus B square. This number is such that this number is denoted by 1 by Z or Z to the power minus 1, and if we multiply the original number Z by this Z inverse, we are surely going to get 1, which is the multiplicative identity. So we have the number 1 by Z such that Z into 1 by Z is equal to 1. So for every number, for every non-zero complex number, we have this multiplicative inverse such that Z into 1 by Z is equal to multiplicative identity. Now the last law is distributive law. Obviously for Z1, Z2 and Z3, if we have Z1 into Z2 plus Z3, then we have Z1 into Z2 plus Z1 into Z3. This is called left distributive law. Similarly, we have right distributive law, that is Z1 plus Z2 into Z3 is Z1 into Z3 plus Z2 into Z3. This is called right distributive law. Now out of this particular number, okay, for a number A plus IB, we have its multiplicative inverse, which is given by A upon A square plus B square plus I into minus B upon A square plus B square. We can find out this number by actually doing a very simple calculation. We can consider a number x plus IY to be the inverse, and then I think how this number particularly comes, you can find it out by yourself. Consider Z inverse to be equal to x plus IY. Okay. So now Z into Z inverse, which is equal to A plus IB into x plus IY, must be equal to 1 plus 0I. Now as we know, this Z into Z inverse will be equal to AX minus BY plus I into AY plus BX. Okay, so this is equal to 1 plus 0I. So we have AX minus BY is equal to 1 and AY plus BX is equal to 0. Now you can solve these two equations to get this as the value of Z inverse. I think you can do it by yourself. Now let's understand what is meant by division rule. Now for given two complex numbers Z1 and Z2, Z1 is equal to, where Z1 is equal to A plus IB we can take, and Z2 is equal to C plus ID, whatever we want. But in this case, Z2 must not be equal to 0. Then Z1 upon Z2 can also be defined as Z1 into 1 by Z, that is, this is the multiplicative inverse of the Z2. So obviously, division can be expressed as the multiplication of original number and the inverse of the denominator. Okay. So simple way to evaluate the division or the quotient is, let's say we have two numbers. So in this case, if we want to find out the division, what the simple rule states is, we can solve this by multiplying numerator and denominator by the conjugate of the denominator. Now consider this example. Z1 is equal to 5 plus 3i and Z2 is equal to 1 plus 2i, and we want to find Z1 upon Z2, which is equal to 5 plus 3i divided by 1 plus 2i. So what we are going to do is, we are going to multiply numerator and denominator by complex conjugate. Now complex conjugate of 1 plus 2i is 1 minus 2i, but we will have to multiply numerator as well as denominator by the same. Now the multiplication of the numerator will be 5 into 1 5, 5 into 2i is equal to 10i, then 3i into 1 is 3i, and 3i into minus 2i is equal to minus 6i square, and denominator is 1 square minus 2 square I square. Now that is equal to Okay. 5, this is minus 10 plus 3 is minus 7i, and 6, I square is equal to minus 1, that's why we have plus 6 over here. And in the denominator, I square is equal to minus 1, so 1 plus 4. So the final answer we have is 11 by 5 minus 7 by 5i. So this is how we are going to solve the division of the two complex numbers. Remember, we have to multiply numerator and denominator by the complex conjugate of the denominator. Okay. So now also remember that most of the identities which holds for the real numbers will also hold for the complex numbers. You can use these identities to solve many problems, right? For example, let's say z1 and z2 are the complex numbers, then z1 plus z2 whole square will be z1 square plus twice z1 z2 plus z2 square. Now z1 minus z2 whole square will be equal to z1 square minus twice z1 z2 plus z2 square. z1 minus z1 plus z2 cube is equal to z1 cube plus thrice z1 square plus z2 plus thrice z1 z2 square plus z2 cube. Or z1 minus z2 cube is equal to z1 cube minus thrice z1 square z2 plus 3 z1 z2 square minus z2 cube. Or the fourth rule, like z1 square minus z2 square is equal to z1 plus z2 into z1 minus z2. So all these identities which are satisfied for the real numbers, which holds for the real numbers, will also hold for the complex numbers. You can use this to solve. Now let's try to solve one or two examples. Let's say the example is to find the conjugate of the complex number 2 plus 3i upon 3 minus 5i into 1 plus I. So we want to find out the conjugate of this particular complex number. So now z is equal to 2 plus 3i divided by 3 minus 5i into 1 plus I. So we will multiply the denominator, two numbers in the denominator first. So that will give us 3 into 1, 3, 3 into I, 3i, and you can go on solving. So the multiplication of the denominator comes to be 8 minus 2i. So the given number is 2 plus 3i upon 8 minus 2i. But again, we will have to multiply numerator and denominator by the complex conjugate of the denominator, which is 8 plus 2i. We will multiply this. So after multiplication, what we will get is, it is 16 plus 28i minus 6 upon 64 plus 4, which is 10 plus 28i divided by 68, which is 5 plus 49 divided by 34. So this is the original number z. Now the complex conjugate of it will be, obviously, z bar is equal to 5 minus 49 divided by 34. Let's try to solve one more example here. If a plus ib is equal to x plus I whole square divided by 2x square plus 1, then prove that a square plus b square is equal to x square plus 1 whole square upon 2x square plus 1. Now how to solve this? See, a plus ib is equal to x plus I whole square divided by 2x square plus 1. So let's solve this. X plus I whole square will be x square plus twice xi plus I square divided by 2x square plus 1. I square is equal to minus 1, so we have x square minus 1 upon 2x square plus 1 plus I into 2x upon 2x square plus 1. By equality of the two complex numbers, we know that the two complex numbers are equal only if the real part is equal to real part, which is a must be equal to this, and imaginary part must be equal to imaginary part. So we have a is equal to x square minus 1 upon 2x square plus 1, and b is equal to 2x upon 2x square plus 1, obviously a square plus b square. Now we can just put these values and calculate. So x square minus 1 whole square upon 2x square plus 1 whole square plus 2x square upon 2x square plus 1 whole square. So if we go on solving, denominator is same, so we add the numerators also. So x to the power 4 minus 2x square plus 1 plus 4x square. So minus 2x square plus 4x square will give us plus 2x square. So we have x to the power 4 plus 2x square plus 1 upon 2x square plus 1 whole square. So we have x square plus 1 x square plus 1 whole square upon 2x square plus 1 whole square. See, all these rules you can use and go on solving many other problems. So that's it for now. Let's see the other concepts in the next video. Thanks.